All right, welcome. This is chapter 11 of the hands-on machine learning book, or said another way, it's chapter 2 of the deep learning portion of the book. So last session, Ryan talked about the basics in terms of the different ways in which you can define the layers, the different components in your neural network, and we talked a little bit about training. And so then this chapter, the focus is on 4 problems once you get beyond toy-sized problems. Okay, so we saw basic training code, and so now we're going to deal with when we do back propagation, vanishing exploding gradients. We're going to deal with reusing a pre-trained model that somebody else trained, because you don't have as much data, or to save time. We're going to talk about better optimizers in order to get your training done faster. And pretty much every week we talk about regularization. So we're going to talk about regularization in order to avoid overfitting. I've got some notes, but happy to take questions as we go. I also wanted to just check and see, are there any questions, any topics people want us to cover? If so, I'll make note of it, make sure that we hit it as we go through the different topics. So I'll pause for a sec just to see, either in the room or online, if there are any particular things you guys want us to talk about today. All right, we'll get started at the beginning of the chapter then. All right. So these notes, pasted them into Slack, and also the link is in the Zoom chat. So the number one thing is, when people started training neural networks, they made a little bit of progress, but as soon as they tried building bigger ones, deeper ones with more layers, they started running into problems. And the main thing is, as described in the first section of the book, is if you look at this blue line, which is the sigmoid activation function, okay, if you pass in a 0 to this function, and then when you're doing back propagation, you're saying, what's the gradient? What's the slope of this curve, such that if I tweak x a little bit to the right, so make it 0.1, tweak it a little to the left, make it negative 0.1, that's going to change my output. Okay. And you can see in this section of the curve, changing your value by a little bit actually will move things by quite a lot, because the slope here is about 1. Okay. But as soon as you get an input value closer to 4 or -4 or further away from 0, you can see that this curve is very, very flat. It's close to horizontal. So that's what they mean when they talk about saturating. Okay. And the idea is that if your gradient descent algorithm says, hey, what if I tweak my value from 4 to 4.1? How does that change the output? Well, the answer is it hardly changes it at all, because the curve is flat. All right. So this means that you're not really going to have a very big effect no matter what you do. And your gradient descent algorithm, if it converges, is going to converge very slowly. You do this once, it's not great. Gradient descent takes a longer time to learn. You start building multiple layers with this kind of curve with big flat sections, and then you run the risk that your model just doesn't learn at all, because basically, as you go through the layers, what tends to happen is your gradients get smaller and smaller. So you do this 3 times, you do this 4 times, and then next thing you know, basically all your gradients are close to 0 and nothing's happening. So this was a problem. We will see in a later chapter these recurrent neural networks, which have a whole nother problem because of the way that they're reusing layers, and so stuff repeats. But anything that's deeper kind of runs into this problem. So one of the first things people realized is that the initialization of the weights on your layers is super important, because basically you want to initialize things so that you're close to this steep part of whatever your activation function is. So if you accidentally initialized it in a way that you give it an input and the output is already 6, you're already at the flat part, and then you run the risk of what they talk about in the book as one of those dead neurons. Okay. So it's very important that you scale your inputs to sort of some known range, and then you initialize the weights so that when you take that known range of input and you multiply it by your initial weights, you end up with values that are sort of in the range that we're looking for. So that's the main thing from the second section. And I think for more than just a casual understanding of deep learning, I pulled this quote out of the book. It says, "We need the signal to flow properly in both directions, in the forward direction when making predictions, and in the reverse direction when back propagating gradients." So when you're first learning and you're just building toy problems, you don't really have to worry about this. But if you're going to spend any time deeper, or if you're going to read ML papers, it's really important to understand that when you're training a neural network, data flows from your inputs to your outputs layer by layer, and that part is usually fairly intuitive, fairly easy to understand, right? You define a layer that has like 3 inputs as weight 1 times the first input plus weight 2 times the second input plus weight 3 times the third input, possibly times plus, an additional bias term. That's the way we define layers. So usually that's pretty clear and obvious. What's not so obvious is that there's also, if you just write it out, there's the math for you take the loss calculated on the outputs of the model, and then layer by layer, you calculate the gradients going back towards the inputs. Okay. And these have different properties, the forward direction and the back direction. One of the simple things to understand is that if you have a node and it has lots of inputs, so what we call high fan in, that means that you're summing up a lot of weight times inputs. Okay. If you have only 3 inputs, you're summing up 3 of those. But if you have 100, if you have 10,000 inputs, then you're summing up 10,000 of these, and you're just going to get a bigger number, even if all the numbers were initialized. Did my bike Did the other mic die? Is that why there was a hand raise?
Yeah, it seems good now.
All right, sorry about that. Um, all right, so I don't know how much you guys missed, but so what I was saying is the key thing is that fan in affects how much numbers pile up and get bigger on the forward pass, and fan out affects how much numbers pile up and accumulate on the backward pass when you're doing back propagation. And most models on any given layer, the fan in, the fan out are not only not the same, but often very different, like sometimes orders of magnitude different. Yeah, question. Yeah, exactly. So if you have an input layer with 256 values, then for the first layer of your model, the fan in is 256. And if you have, let's say, I don't know, I'll just use an arbitrary small number, only 10 nodes there, okay, um, then those 10 nodes in the next layer, let's say it's shrinking even smaller and it goes down to 4 nodes, then the fan out is 4, but the fan in is 256, and they differ by 2 orders of magnitude. Okay. And so it's possible to have in different parts of the neural network much higher fan in than fan out, or much higher fan out than fan in. And it's just counting the number. If you were to physically draw each node as a circle, it's just counting the number of lines going in is the fan in, and counting the number of lines going out is the fan out. Yeah. So the question was, what if it's not a fully connected network? So um, you still are doing the equivalent thing, but yes, you obviously have to count it slightly differently. But basically, the idea is any node that uses the output of this node in its calculations is going to be in the backward pass is going to be passing a gradient to you. So the more places where you're sending this, the more that gradient is going to accumulate and pile up. Okay. So a very common thing we see uh, is that the number of nodes tends to sort of shrink towards a bottleneck in the middle of a neural network. And so it's very common in the early layers to have fan in be higher than fan out. So the good news is that most of the time, whether you're using PyTorch or using Keras, you don't really need to worry about initialization. It's going to have a default initialization, and you can just use that. So it's a good concept to understand. And um, uh, one of the things they talk about is that in the Glorot initialization, what it does is it just averages the fan in and the fan out. So if the fan in is 100 and the fan out is 10, it says, what's the average at 55? And that works pretty well for medium sized neural networks. One of the things that I personally find interesting is that you can study the dynamics of the fan in and the fan out much more closely. And there have been some research papers that I've read where people do that and they say, hey, we're actually going to do smarter, more custom things. And if I remember, I'll make a comment about the Muon optimizer, which actually does do this. Did you want to add something?
Yeah, so one piece that I want to add about initialization. So imagine your first guess, the model has never seen any data, never been updated or anything like that. It has to send that data through all the layers, and then it's going to make some guess to start. So imagine you start your initialization with every weight is around 2 or something like that. So at every point, it's like doubling whatever its input was. And so it's going this layer double, that layer double, that layer double, depending on the fan in and fan out. But imagine you get all the way to the end and your initial prediction is going to be 10,000 or something, depending on what the prediction actually is. And you want it to be closer to what your actual like starting point is. If your outputs are centered around 0 or something like that, you probably want it to be closer to 0. And so the initialization, like if you're training a model, you can see sometimes like if I initialize this really badly, then my loss starts at 1,000,000. And if I started at a reasonable value, then it starts closer to, I don't know, 1 or something like that. So the initialization can have a huge impact on your starting point. And then if you just set it wisely, then you learn much better and you don't have dead neurons and you don't like start at some ridiculous value. So that's my intuition of it, at least. Like you want it to start kind of like initially making predictions that are at least in the ballpark of whatever you're trying to predict.
Yeah, that's great. I think the first neural network that I ever built and trained, they purposefully set the exercise up so that we would fail. So we had this color image, and I don't remember if we were doing like binary classification, like cats and dogs. And then if you're familiar with JPEGs, they have values between 0 and 255. So we took the image and we passed it into this nice neural network that we built. And then along the line of what Ryan's saying is with the initializations being around one-ish or whatever, our predictions were like plus 255 or like negative 255. And then that went through a sigmoid in order to turn to a value between 0 and 1. But so all of our initial predictions were like 0.999999 or 0.00001. And when you trained it for just like whatever 100 epochs, it looks like absolutely nothing happened. And so then they're like, yes, this exercise was designed to show you the importance of having the right scale on your values and your weights. And so then we just divided all of our inputs by 255 and then everything worked great. So can you use a microphone? I don't mind repeating, but
Hi. Have they come up with some kind of a heuristic as to how to do the initialization so we don't end up with egregious values? I mean, a formula would be good, but it's a little too much to expect. Something that could give us some kind of an idea.
Yeah. So for almost all problems, if your input data is between 0 and 1 or between -1 and 1 predominantly, then the default initialization in Keras or in PyTorch is all you need, and it'll be fine. Okay. So yes. So this is telling you about this important concept. Fortunately, the defaults are now to where people have been training these for a few years, and as AI has gotten more popular, they figured out like here's a set of settings that is fairly robust. It's like I think about like cooking recipes, right? Like if you're making chocolate chip cookies, you not only want a recipe that tastes good, but you ideally want a recipe that if you mess things up and you add a little bit too much or a little too little of something, it doesn't completely break the recipe. You don't want it to be super brittle. So the good news is that initialization these days is typically not very brittle. All right. So that was one concept. Again, it's important to understand the background for this, but fortunately, you don't need to do too much with it these days. Another important concept is the activation functions. So I showed the picture of the sigmoid at the beginning, and it's that S shape, and it's very flat when you go farther to the right and farther to the left. So the book didn't have a picture of ReLU. It was mentioned in the last chapter. Here's a picture of leaky ReLU, and the difference between leaky ReLU and ReLU is that to the left of 0 for all negative values, ReLU is exactly 0, so it's right on the x-axis. And the really good thing, one of the really good things about ReLU is that you'll notice that for positive numbers, the slope is always 1. You never reach a saturation point. There is always a slope. And so for any positive value, nodes with ReLU will always learn. The other, by the way, the other thing that's nice about it is it's really simple to calculate. So it's super duper fast, which was more important in earlier days. Now that we have really fast GPUs, it's a little bit less important. The idea of leaky ReLU is that instead of having the negative part be completely horizontal, which has a gradient of 0, meaning that no learning is possible whatsoever. So as soon as you end up in the negative region, when gradient descent says, what if I move 0.1 to the left? What if I move 0.1 to the right? The answer is identical. There's no motivation to move in any direction. Okay. So leaky ReLU solves this by saying, well, instead of having it be completely flat, we'll have it be slightly tilted. And so now you actually have a motivation to move a little bit to the left or a little bit to the right. It might go slowly for a while, but once it gets towards close to 0, now you have the potential where the difference between negative 0.1 and positive 0.1 actually makes a much bigger difference in your outputs. And then the model can learn, again, which way to push the weights in order to get a better answer. So that was an early thing that people realized, avoid flat things. Now we've gotten a whole lot fancier, and we have these these functions like, I don't know if people say GALU or JLU or whatever, but I say GALU. It's Gaussian, so it's a hard G is the acronym. But GALU, Swish, and you'll see some of these other things in research papers. They have very slight differences, but they all have this property that they're curvy, so they don't have this kink in the middle that ReLU and leaky ReLU have. This kink means that the derivative is well, technically it's not defined. It's not smooth. Whereas because all of these, whether you look at whatever it is, the blue, green, orange, all of these you'll notice are smooth curves. Okay. And so that means that the derivative is also nice and continuous, and so it doesn't have any big jumps, and learning tends to happen in a nice, I'm not sure exactly what the word I'm looking for is, but because it's continuous, it's very predictable. It doesn't have any weird jumps in it. Okay. And so you get smooth progress. It could be fast, it could be slow, but you get sort of a very predictable, smooth progress. The cumulative distribution function. All right. Thanks for the fresh batteries. Yeah, so if you look at like modern LLM papers, you'll see people will say we switched from one of these, Swish to GALU or SILU or whatever. And at first blush, if you look at any of these, they all look the same. All right. They all go up to the right, just like ReLU. So they all have a slope of approximately 1 for all large numbers. Okay. They're all curvy, so they don't have any kinks in them. And then the interesting thing is that they all dip down, but then eventually come back. And at very large negative numbers, they hug the x-axis. So early activation functions like sigmoid, tanh, ReLU, leaky ReLU, they all have this property where the function, when you go from left to right, was monotonically increasing. And people thought that that was a good thing. And so these functions, if you look here, like at the blue line, it's the one the easiest on my eyes to see. You can see that it like somewhere around, I don't know, negative 0.7 or whatever, it has the lowest value. And then it actually comes back up closer to 0 as you go further and further to the left. Yeah, question? So the question was like, does that mean that things are worse if you're below this bottom of the bump, like say at -2? It doesn't necessarily mean it's worse, but it it means that potentially if you're to the left of the bottom, then it's pushing things to the left in order to go up. But it could go up a lot more. We know it could go up a lot more if you actually push it past that bottom and to the right. And so I think that's the intuition why it's not like a parabola that's just symmetric. And so whether you go left or right, if you know that if you go left and you keep going left, there's only so much that you can go up, right? So I think that's why for a long time people never really considered this was a plausible activation function to use. However, in practice, what people find is that these functions work really, really well. And I'm not really sure if there's more recent research. When they first came out, I saw some people talking about the fact that if you just imagine pushing a bunch of numbers, like whatever, -2, -1.9, 1.8, da, 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 like if just every 10th or whatever, and you push it through a function like ReLU or whatever, then basically what's happening is you're just sort of scaling the numbers. So in some places where you have a steeper slope, you're spreading out the outputs a little bit, and where you have close to zero slope, the numbers are really tight. But with this, because the slope actually changes directions, if you just imagine taking like 40 points at tenths between -2 and +2, there's going to be a place where there's actually a fold, a loop in the values. And that actually is far more complex and expressive than just simply stretching and squishing things a little bit. Okay. Now, that could be a bad form of expressive, or that could be a good form of expressive. In practice, it seems to work really well. It seems to be a good form. So basically, if you're building small learning projects, ReLU works really well. It's fast. When you see very large models, state of the art, pretty much these days, everyone uses one of these curvy ones like Swish. I again, I don't know if there's newer research. I can't explain why, but it does seem like that this complexity could be bad, but it ends up working quite well. Let me just check the chat real quick. I think it's just audio again. Okay. All right. So the thing I'll say about activation functions is, again, that it's good to understand these things. If you're not doing state-of-the-art research, odds are it doesn't really matter too much if you're doing something, whether you use ReLU or whether you use something like GayLU. But I would pick like one of those two and not one of the ones that we haven't heard about as much. So yeah, did you pass the mic? Did that one die? All right. I think the people last week had a presentation and used all the mics, and so when we got here they were all working, but they're all like
That's all right.
low battery.
So, is there any possibility of any of these activation functions help us escape from a local minima or something like that? Are there any studies done so that we don't get stuck in a local minima, which is so high that our error is never mitigated?
That's a great question. So I do think that at the end of the day, we want activation functions and we want a learning algorithm, our gradient descent, to not get stuck too easily in local minima. I cannot tell you firsthand what the dynamics are, but yes, I would assume that the two things that you generally speaking don't want with a neural network is you don't want a node that's what they call a dead node, where basically tweaking the inputs a little to the left, tweaking the inputs a little to the right makes almost no appreciable change in the loss function. Therefore, it just basically doesn't move very much at all. And effectively, if it's never going to move, it's never going to change, it's no longer learning, it's quote unquote dead. Okay. So that's one thing you don't want. And the other thing is you don't want to get stuck in a local minimum. But but it would be very complex. And I can't speak to the specifics of whether or not these curvy ones help us avoid getting stuck. There's a lot of dynamics, between this and the learning rate and all these other things that we do when we're actually doing the training.
So the stochastic gradient descent is our best bet.
So we're using a variant of stochastic gradient descent for all neural network training today.
Yeah.
Yes.
The XGBoost probably, I don't know. I'm just using the buzzwords randomly.
Yeah. So we are there are no closed form solutions. Like for linear regression, basic linear regression, there's a closed form solution. There are no closed form solutions for large neural networks. And so we just train them using optimization, using gradient descent.
Okay, great. Thanks.
Tom, can you pass that?
Have any local minima? Looking at them, I don't feel they can have. Like we were talking about all the Galus, it doesn't look like it will get stuck in any local minima because they are monetically increasing or decreasing. None of them has a concave and tips like that.
Do you want to say that?
Yeah, so we're not really talking about local minima in terms of the activation function. Like the activation function, they have that curve. We apply that to whatever's going into them. So that's always the same. But it does have what we typically talk about is like the loss function. The loss function is going to say we have these weights, we pass through the model, we get this loss function. If we move around the parameters, how does that make a bowl of the like loss? So we're more concerned with the curvature of the loss than we are of the actual activation functions. And so those do have an impact on the way the loss forms. Yeah. So it does have an impact, but it's like some complicated, like I don't even know how you would compare a swish from ReLU from something else. Like it does definitely yield a different outcome, but I don't know the math behind like what's going to lead to less local minima and stuff like that.
Yeah, thanks. That's what I was trying to say, is that it's a very complex relationship. And if you think about a deep neural network with multiple layers, right? Even if we are, one of the earlier questions was, what if we're to the left of -2, we're somewhere over here, okay? And maybe the dynamics are that if we're trying to increase the output, the gradient tells us that we would move to the left, okay? But the thing is, the layer in front of us is also learning. And so it's entirely possible that its values, its output would get larger and would push us to the right, even though that's not necessarily the direction that our gradient does, right? So so there's a lot of dynamics is what I'm saying. And the higher principles to keep in mind are, what we talked about. One is if you scale your inputs and you scale your weights in a reasonable range, then you tend to start out in this sort of -101 range. Okay. And so that's the good range where there's learning happening and there's interesting things. And it is also true that most state-of-the-art models these days are very large, and they end up sparse in the sense that not every single neuron is heavily contributing to the answer. There end up being a bunch of nodes that you could zero them out, you could delete them, and the model's performance would be almost identical. And that's I think that's something that we just happily pay the price, because if you said, I trained this model to do cats versus dogs, and my model has, let's say, 100 nodes, half of them you can delete and I'll get within 1% performance. If you trained a model that had only 50 nodes, you wouldn't actually get the same thing as your 100 node model, just the half good ones. You'd still get a model that 25 of them aren't doing anything and 25 are. So we basically just pay that price as part of the cost of how these neural networks work. And that's one of the properties, is that neural networks train really well. You can do different random number seeds, you can do different random initializations, and you get almost the exact same accuracy. So there's something about the architecture, about gradient descent, that works really, really well. There are people still researching to see if they can really get at the core, the nugget of why it's so easy. But the great news right now is that if you have a problem, this easiness to train, easiness to learn is something that you can just lean on, even if we don't really know all the theoretical reasons why it is easy. So there's a question in the chat. Are we fixing vanishing, exploding gradients problems with different activation functions? And one of the key things in terms of the vanishing gradients is all of these activation functions, you'll notice for positive numbers, they never saturate. They have this thing where they're approximately slope equals 1. That's a very key thing in terms of not having these vanishing gradients. I think that's probably the biggest thing, that these particular activation functions way better than sigmoid. Okay, sigmoid, as soon as you leave that range right near the center, you're in a very, whether it's positive or negative, you're in a very flat area. Did you want to add anything to that?
Yeah, so the activation functions have an impact on the vanishing, exploding gradients. The initialization has an impact, the batch normalization, like all of these things have implications for it. You have to think like this, the whole system is like echoing throughout itself. And so if you normalize and you say everything has to be between -1 and 1, that has different properties. If you say I use this different activation function, then that has different properties. People have generally figured out like what Ted was saying, like this safe recipe where it's like you use the defaults and you're not really going to have problems with it. Like if you have something really strange in your data, or you do something really wonky with your network design, you might have these issues. But in general, like if you use the defaults and the stuff that they mentioned here, you're going to be safe from exploding and vanishing gradients.
Thanks. Yep. And that's actually a good segue to the next section of the book, where they talk about batch normalization. So it was mentioned, I think, last chapter and earlier, we talked about scaling your inputs. Okay. I gave the example where put pixel values between 0 and 255, and that was not really what the defaults of the neural network were expecting, and things didn't work well. As soon as I divided them by 255 and they were values between 0 and 1, then things worked well. That's okay for the very first layer of your neural network. But what happens if the first layer of your neural network is outputting values like 255? Now your second layer might be unhappy. And so that's where the idea of normalization between layers came in. And the first really big successful one is called batch normalization. I'm not going to like repeat the formula and whatever, but basically the idea is that it's scaling your data, and you can put batch norm anywhere you want. So you can put it between the first and second layer. You can put it between every layer, between the second and third, between third and fourth. And then what it will do is it'll ensure that your data cannot just be some ginormous value like 255 going between adjacent layers. Batch norm does actually learn what is the good scale that you want. So there is a parameter that batch norm learns. And so you don't have to hard code, oh, I want batch norm to set all my value, the majority of my values between 1 and -1, or between 5 and -5. It'll just learn that on its own. And so in that sense, batch norm is pretty easy because it's kind of set and forget. I personally find batch norm kind of weird. because you're averaging values when you're training across your input batch. And your input batch could just have all sorts of random things. And if your batch size is small, then in particular, if your batch size is only 4, like what the heck? We're only averaging 4 things. So batch norm does calculate an overall data set average, which is used once you're done training. I've never really understood. I don't know if there's a paper that actually says, what if you just use that overall average instead of the batch average? But people don't seem to have messed with it. And the book mentions that it does add a little bit of randomness to your model, which does seem to help with the overfitting. So I don't know, who am I to question it? This section, this chapter doesn't really talk about other kinds of normalization layers, but certainly whenever you talk about LLMs, you will see some other ones. In particular, you'll see like layer norm and RMS norm. And the idea there is, in an LLM, you have many input tokens. Okay. And so you're guaranteed that if your input is fairly long, that you're going to have a lot of those input tokens, and you don't have to actually use the batch of different inputs. You can actually just look at all the different input words, the input tokens. And so you can use that dimension in order to average things instead of having to worry about the batch direction. And so those work fairly similarly, slightly different concepts in terms of whether they center it on 0 or whether they learn how to have the mean, the average, be something other than 0, be offset. But the key idea here, just like we've been talking about, is when you initialize the weights, you're initializing them on a scale that you're expecting your inputs to be a certain magnitude, and then you want your outputs to be a reasonable range for your activation function. Okay. And since these normalization layers all have parameters where they learn the scale that they're going to output, they can basically adapt. And as your model is training, they will continuously try to like shrink your data to the point where it's fitting that range, and potentially also the reverse. When we talk about vanishing gradients, they can also increase your data so that you actually have bigger gradients, so that the gradients aren't just falling away and disappearing closer and closer to 0 until potentially you actually get a floating point underflow, and the number's so small that your floating point can't even represent it, and it literally becomes 0. So the question is, will the batch norm introduce its own weird kind of bias? That's how I feel about it. It works really well. So empirically, yes, earlier on when we talked about optimization, we said that, hey, gradient descent has these properties of convergence, and whether you do full batch gradient descent or you do stochastic gradient descent or you do mini batch, people have proved that like, mini batch gradient descent will converge to a good optimum and blah, 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 blah. Technically speaking, as soon as we throw batch norm in there, all those proofs go out the window as far as I know, because it's got its own idiosyncrasies. In practice, however, it works, and the idiosyncrasies seem to be small enough that it doesn't really change the overall dynamics.
So what I have learned is it actually approximate the batch mean is approximated to the global mean and the variance. We can say it by the large law of numbers, or CLT, where when you take a lot of samples and the mean of those samples would be population mean. So by that, it actually works here also. So most of the time, the approximation is good to take, because we don't have we have huge data. We'll be working with a lot of batches, and approximation would end up with the same mean and variance. This is what I have observed.
So there's a question in the chat. Somewhat confused by the note that batch norm is only used during inference/test time. I thought you do use the mean standard deviation during training and use a moving average computed during, yeah. So let me reread my note and make sure. Um, uh, yeah. So what I'm trying to communicate with this note is that we are actually calculating an estimated global mean and standard deviation across our entire data set. And that's what we use for inference at test time. Okay. We have those numbers lying around, yet we still don't use those during training. We just use the actual batch mean, which could be much noisier than the estimated data set mean. And so I don't know. I'm guessing somebody at some point did try swapping it out and using that calculated mean instead. And I guess people like the little extra noise that the batch mean introduces.
I just looked at the PyTorch documentation because I wasn't sure either. I hadn't really looked at that detail before. So the way that it works is during training, it's looking at the individual batch mean and standard deviation, and then it's accumulating that in some running mean, running standard deviation that's only used at inference. So it's kind of trying to approach what's the actual mean and standard deviation of the whole data set. But at training time, it's just saying individual batch, individual batch, individual
Right.
batch, individual.
Yeah, and that's what the book says, and that's what always kind of confused me is that you would think later in training we could just use this moving average, mean and standard deviation that we've calculated. We're going to use it once we've stopped training for predictions. So like, why not, use it now? And it just seems like my guess is that people actually like that little bit of noise introduced by the batch, in the same way that stochastic gradient descent is a little bit noisy because you just pick a random batch of data points. And so if I'm doing cats and dogs, maybe this one batch just has 12 dogs and 4 cats, and it's not split half. Maybe one batch has 2 hairless cats, and that's like a very, very weird signal that we're going to get. But in the grand scheme, once you do lots and lots of training, all this stuff seems to average out. And I think batch norm is the same thing.
So one thing in the PyTorch implementation, I don't know as much about the TensorFlow Keras one, is you can have that setting. So at inference time, you can use the running mean, or you can just do the actual this individual batch. One thing that I'll point out that people figured out the hard way back in the day using Keras TensorFlow stuff was you're at the mercy of whatever the estimate is for a given batch. So if you go, I have a batch size of 16, everything's happy. If you go down to a batch size of 1, then you can get some very strange behavior because every batch is always going to get mean 0 standard deviation 1, and that can just totally break things. And so one of the weird side effects of that was when people were trying to do multi-GPU training, if this one gets a batch of, if you have a batch size of 4 and you have 4 GPUs, each of them getting a different copy, they're each going to have a different mean and standard deviation. And then it can actually mess with the convergence of your model. So just random thing that I ran into back in the day. So batch norm has been replaced in many places by layer norm and RMS norm and other things that people have figured out. But that's like the core building block that they're all variations on top of.
Awesome. Yeah. It's not working. Yeah. Yeah. Sorry, guys. We're having trouble with all the mic batteries. But yes, the comment was batch norm really can be helpful with overfitting. We haven't talked about dropout yet. That's coming up. But basically, it is adding some randomization. It is adding some noise. And so that is a potential positive of batch norm. So I would say the TLDR is if you think batch norm is a little weird, you have good company. It is a little bit weird. Okay. But if you consider the alternatives, you've built a deep neural network, it has 20 layers. One option is don't use batch norm and run the risk that your outputs are going to be really large positive, really large negative numbers, and it's going to mess up the layer after it. Or use batch norm, even though it's a little bit weird. By far, the lesser of the two evils is use batch norm, even if we don't 100% understand all the properties of what the heck it's doing. Okay. So Ryan mentioned like, hey, sort of like the standard recipe. So you will see if you look at it, if you download, different models that people are using, you're going to see a lot of this normalization layers in there. And again, if you follow that recipe, you don't have to really know exactly what batch norm is doing. It's okay if you think it's a little bit weird, but it still just works. And again, it's highly tolerant. You don't have to have the perfect architecture. You don't have to have some very super specific ratio of the number of nodes in this layer to that layer in order for batch norm to work. No, you can just pretty much stick batch norm anywhere and it's not going to break anything. Okay. I didn't even mention, in the book, they talked a little bit about like some special activation functions, ELU, that if you like initialize your data to be Gaussian and this and that, then it has these mathematical properties. That again is something that I consider to be sort of brittle, that you have to like really do A and B in order for either of them to work together. And that's why generally people don't use it. It's like, no, use something that just kind of works and has a very flexible wide range where it's easy. You don't have to worry about it.
One extra piece about the batch norm. So in the previous chapters, we've talked about normalizing your input. So you want to rescale them, mean zero, standard deviation one. You can go and you can calculate that for your entire data set, but sometimes that's actually difficult to do if you have a lot of images or just a million rows of data or something like that. The process of actually finding the mean and standard deviation for every single feature can be annoying and slow. And so one of the hacks that I've seen is you just make your first layer batch normalization. And so it's seeing this batch of data, it's normalizing it, it's doing that same exact process. So it can be kind of a shortcut and a hack to get around, like, I have so many rows of data, I have to calculate this ahead of time. Instead, you can just do it on the fly with a batch norm layer.
That's great. Yep. And then after it's seen, whatever, few thousand inputs or whatever, it's already got a pretty good estimate. It'll just keep getting better. All right. So in this first thing, we're still on the topic of like, how do you manage your gradients? Because you want the forward and the backward directions both to have good values in order to have good learning happening. The last topic here they mentioned is gradient clipping. And I would say that this seems like kind of a drastic option to do, where you basically say, oh, my output is really large. And I kind of know that, like, -1 to +1, -2 to +2, sort of the happy range. So I'm just going to arbitrarily say, if you see a number bigger than 5, if you see a number bigger than 10, if you see a number bigger than 20, just whack it and cut it down to, have some max absolute value. So I'm not going to allow anything bigger than ±5 or whatever. So I would say that this is probably not something that, if you're playing around, should be one of the first things that you go to, but you shouldn't be shocked if you see this in a model that you download. It's I wouldn't say it's like 50% common, but it's not so rare that, like, you're unlikely to ever see it. Anything you
on gradient clipping, that's something that I use very often as just a safeguard against weights and other things blowing up. because it's very annoying when you go, okay, my model was training successfully for 4 hours and then randomly it got some weird spike and it just blew up the whole model and now it's just infinities or nans or whatever. And so I don't use it all the time, but if I do a training run and it blows up, one of the first things I go for is gradient clipping, just as like this is minor protection for something crazy happen. I have something bad in my data or something else weird going on.
That's cool. And then do you set the clipping value relatively large, not super tight?
Typically, if I start with typically like 10, and then I think that's just the default value. And then if I still have explosions, then I maybe go down to 1. And typically that will limit your learning rate a little bit. It might converge a little bit slower, but in general, I haven't had problems with that.
Yeah. So if you look at these curves, right, plus minus 10 is way outside of the region that we're showing here. So it's pretty safe in the sense that your normal activations won't typically be that extreme. And by the time they are, the difference between 10 and 12, I mean, whatever, it's just still really big. Or 10, negative 10 and negative 12, it's still really negative. So it's not that much difference between the two. So what's your questions? Yeah, so what Ryan was talking about is normally we say scale your data properly, okay? So if I have images, I know that the pixels are between 0 and 255, and I can purposefully decide, do I want them to be between -1 and 1 or between 0 and 1? So just dividing by 255, they'll all be between 0 and 1, okay? But if you have some sort of scientific data, whatever, and you don't necessarily know exactly what all the values are, what is the average, okay? And if you have millions of them, whatever, you might not want to try to calculate that yourself. So he was saying the trick is if before your inputs, the very first layer of your model is a batch norm, ultimately it is going to be calculating the average for you, but you just don't have to do it in advance. During training, it'll just get calculated for you. And so that's just a way of saving you from having to manually scale the data. I'm sorry, you're not asking a question with a question mark at the end, so I'm not quite sure what if you. Yeah. Okay. All right. So just checking on the time. I'm going to speed things up a little bit here. But again, this was probably the most dense part of it. So I think it's good that we spent time to understand some of these fundamentals, some of these dynamics. And again, the key thing is we want good data flow in the forward direction, which is usually very visible. And we also want it in the backward direction, which you have to do a little bit more work. That's usually not as explicitly stated because the forward direction is what's defined by the layer. The backwards direction, you kind of need to ultimately have the loss function and then kind of work things backwards. All right. So the next concept is using pre-trained models, pre-trained layers. The book words it as pre-trained layers. I tend to think of it more just in terms of pre-trained models. But technically speaking, when you use a pre-trained model, most of the time you're tweaking it slightly. So for example, if I want to do an image classification thing that does cats and dogs, and if I take some model that was pre-trained to classify images for something else, it could be people, it could be whatever, then we're minimally at least going to be changing the output layer. So the output layer might originally have been, again, whatever these different people things are, whatever, and so if we're doing cats and dogs, then we might have a binary classification head that we put on there. So I think the key thing here is, with how popular deep learning has become, and how many people have been researching and training models these days, like, you're almost always going to be able to find a pre-trained model, and you're not going to have to start from scratch. So again, it's good to understand the building blocks, but typically you're not just going to be like, well, let me define a layer and let me think I'll put 50 nodes in it, and then the next layer I'll put 100 nodes, and then the next layer after that will have 30. So that's not a very, very common practice. Yeah, Jacques, did you have a question?
Yes. Can you hear me okay?
Absolutely.
So I read this before and I had a kind of a crazy question because when we first talked about it, and I reread a book about deep learning by John Keeler, um, all the models that's been made so far that's been trained, they have a bias. So if we reuse a model previously with the biases, won't we just transfer that bias to our new models as well?
Very interesting question. So so if you let me try and give you the shorter answer. So if I take a model that was trained to I don't know, to tell the difference between dogs and wolves, okay, and I'm going to use it to tell cats and dogs, then predominantly the way the mental model that I have is, you're reusing the lower layers because they have good feature extractors. So maybe early on it's detecting lines and textures and different things like that. And then in the middle layers, maybe it can detect sort of the shape of ears or eyes, or the color of things, what the tail looks like, right? So generally speaking, that's the idea, is that we're reusing those lower, and again, images is just has nice, easy things to describe. It doesn't have to be an image model. But so we're reusing that ability to extract features from our data. And so then when we have training data that we train it on, generally speaking, we're not expecting to be importing a whole lot of biases. It's definitely not going to be zero. For example, if I'm trying to think of like a silly example, but like if you have something dramatically different, like a model that's trained and all it needs to do is look at the color of the animal in order to tell if it's an A or a B, and you have a problem, and what you want is to and it really depends on the shape and not the color at all, then you could say there's a little bit of bias there in terms of like focusing on color versus focusing on shape. But the reality is, despite all of that, people take models that are trained to tell like people from cars, from cats, from dogs, and they reuse those on X-rays, which is like black and white and dramatically different. So so while I think that is a concern, generally speaking, I don't think that's a big deal. And what people are really leaning on is taking advantage of the fact that this model was trained and it's doing a good job extracting features. Yeah, did that answer your question?
Yes and no, but can I ask a follow-up to what your just statement was with another
Sure.
question in a sense?
Yeah.
So if most of these models that have biases in them, and we extracting the top layers from them to try to improve the models we have, but we use them for a totally different situation, the likelihood of the outputs that we have, even though we're using a bigger model to a model to do that, we still could necessarily get different with again different data, or still transfer those biases or develop even new ones because we're using a different set of data, but we're using the same type of parameters. Isn't that more dangerous or more work on our end in a sense? Again, when I read this, I was waiting till we got this chapter because it was like really confusing, but also like I had a lot of these questions that I was thought about that's being used today, and I want to see if there's ways around that.
Yeah, so to be clear, when we talk about transfer learning, typically we are reusing some of the lower parts of the model, possibly a lot of it, okay? And we're replacing the top of the model. So at a minimum, the last layer. So when you talk about um, biases, so I think about something like, hey, somebody built a model and they were predicting prison sentences for criminals or whatever. And so one of the things that people notice is that, well, when you train that model on historical data, the judges may have had some actual biases in the lay term, not just in the technical computerese term of bias, right? That biases that certain people, the way they looked, whether they were rich or poor, whether whatever, that they were handing out different prison sentences. And the models learned well, and they imitated whatever the biases of the judges that they were trained on had. Okay. So if judges tended to simplistically give shorter sentences to women, then the model gave shorter sentences to women. Okay. So the thing is, if you then take the lower layer, that wasn't a neural network, but if you take the lower layers of that model, all that's doing is extracting features in terms of age and this and that and combinations of things. But you're still training your prediction head on whatever your new data is. And so if your new data doesn't have a bias between men and women, hopefully that's not really going to play into your final model. Like I said, if you do something completely different, like for example, hypothetically, let's say that data set for the prison model had an input which was, do you like broccoli? Okay. That input may have been completely ignored by the original model because it wasn't predictive at all. But if you decide you're now using this for some medical thing and you have questions like that, it may turn out that things people eat and don't eat are somehow correlated with things going on in their body, and that they would be useful. So the fact that that model was completely ignoring those features may hurt you because ultimately you want those features. But I think the best example is people take image models that were based on color images and classifying things like cars and people, and they use them on x-rays, and it actually works pretty well. So that's a case where like we really are transferring to a fairly different problem.
Okay. So just to be clear, and I'll let this go. Just make sure, like the model we're using, that it to be more effective, completely use it for what you're training on for something completely different. And as far as like the outcomes that you're trying to predict, so like your example, you said prison sentences, and then he was selecting women might be more were not given longer sentences than the men. If you're trying to use that for, I guess, job selection, that would be a bad model because it might have biases towards men and women. But again, if you use that for like, selecting the type of dog you want to have, that would be a better use of that particular model. So you have to really research the model. What was it designed around in order for it to use for whatever you're trying to do? Correct?
Yeah. So I think not exactly. Sorry. So what I'm trying to say is that by reusing the lower layers, we are reusing the features that is it extracting. Okay. So we're not reusing what it does with those features necessarily. Ideally, we're not reusing that at all. We're just reusing that it finds those features. Okay. So for example, I'll try to give you like you have a model that does dogs versus wolves as a binary classifier, and then you want to do something that's like foxes, versus I don't even know, whatever, right? So like it's not, the new model is unlikely to inherit any biases about what makes a dog different from a wolf. What it's going to do is it's going to say, I learned from the original model how to tell texture of fur, shape of eyes, size of ears, these kinds of things. It's not going to learn like specifically big ears, right? It's just going to learn that these are the kinds of features that I'm looking for. And to use image models, they tend to have very similar things in terms of I'm learning shapes and textures and whatnot. So I think broadly speaking, generally, there's not the danger that you're raising. What you should think of transfer learning is as I'm using a model that has learned, instead of me manually extracting features. In the very early part of the book, we talked about, oh, you're doing house prediction and you have whatever number of bedrooms. No, maybe at some point you want to do number of bedrooms times the square footage as a feature. You don't have to do that with neural networks. They're manually figuring out these features. And that's the part that we're using, not necessarily reusing the logic of how they come at their answer, because at the end of the day, when we're doing transfer learning, we're not talking about, we just take this old model and we start using it for the new thing. We do have to have some amount of data that we're training it on. And so we expect that the model's going to learn the proper answers, the proper biases based on the data that we are actually training on. I hope that helped. All right. So for time, I'm going to move on. I have one note here that I added. Here's a diagram where you can see they talked about there's some different strategies where maybe you say, hey, I know that the lower layers are, like we've been talking about, the features that I'm more interested in, and the upper layers are maybe more the logic about how to use those features. So maybe I'll freeze the lower layers, don't let those weights change, and I'll just let some of the upper layers change. And so that's kind of along the lines of what we've been talking about. In practice, though, oftentimes you could just simply let the entire model train and it works just fine without doing any fancy freezing strategies or partial train and then change or whatever. And then intuitively, if you train the whole model, then like we were talking about, if there's some feature that it hasn't really been paying attention to, it is possible for in the learning that you do on top of this transfer learning that it'll learn to pay attention to things that the original model maybe wasn't paying as much attention to. I also wanted to just add this note here because this confused me at first. You will hear words like top, upper, lower, whatever, when we're talking about the layers. And if you see this diagram here, which this is about like freezing and stuff, but regardless of whether it's about that or not, you'll notice that the inputs are at the bottom of the diagram and the outputs are at the top of the diagram. And this was an early convention with neural networks. If I'm creating a generic flow chart or whatever, usually I do it the other way. The inputs would be at the top and the outputs would be at the bottom. So just know that this is the convention with neural networks. And so when somebody talks about, I replaced the top layer, they mean the output layer. Okay. And when we say keep the lower layers, they mean the ones closer to the input. And then occasionally, because you're doing a paper or whatever and the diagram doesn't fit, then people make them sideways. And so data flows from left to right, or they do. But it doesn't matter what the diagram looks like. If people say top layer, they generally always mean output layer. And so that I found that very unintuitive when I first started working with neural networks. So I thought I would just throw in that warning. All right. I haven't focused too much on code in this chapter. For a lot of things, it's just like if you know that there's a thing called a dropout layer, a batch norm layer, then you just say like, you find out the exact name of it. Is it batch norm or batch normalization? You get the exact syntax, but if you understand the concept, then you basically can just drop in these layers. Here I wanted to show this snippet where they said, hey, we're going to take this model and we're going to take everything but the top layer, everything but the output layer that does the predictions. And so you oftentimes will have very simple code where you say, I'm going to take all the layers except for the last one. And so this is just using Python indexing, where we say, right, :-1, and that means everything but the last. And this is a pretty common thing where basically you could say it has a bunch of layers and you can just index into those layers. So the input layer is layer 0, the output layer is -1, blah, 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 blah. And you can just, you can easily do sort of a Lego block connecting of things just by picking layers and connecting them together. So, so just wanted to show that the syntax for working with this stuff is generally speaking not too hard. Obviously, if you're dealing with a highly customized model, then you might need to write a little bit more code. But for a lot of models, you'll just see they've got piles of layers that they just sort of stack on top of each other. Okay, 2 other concepts that I think are really cool concepts you should know about, but you're not likely to actually be using unless you are like at a giant lab and you're trying to do state-of-the-art research or something like that. One is unsupervised pre-training. And so this is where you can take a pile of data and you can use these unsupervised techniques in order to basically say which things are similar, which things are different. And again, this is about learning features. And so if you did this with images, you might actually be able to teach a model that some things are different colors, some things have different textures, some things have these round things that are eyes, even without any labels. Okay. This is generally pretty hard to do well. And so this is why you're unlikely to do this on your own. There's also training on auxiliary tasks. This is done all the time. But again, in the real world, you're unlikely to do this on your own. So many times, one of the best examples I can think of is the BERT-like models that we've used for a while that are really good at understanding sort of sentiment and things like that from sentences. The original BERT model was trained to do 2 things. If you deleted one word, predict what was the missing word. And if you gave it 2 sentences, figure out whether those sentences actually came consecutively from a document or whether you picked 2 random sentences that were not consecutive. Neither of those tasks is really how anybody uses BERT. What they do is they say like, oh, I have reviews from my restaurant on Yelp, and I want to know which ones are positive and which ones are negative. And BERT's very good at doing that, even though the auxiliary task that it trained on had really nothing to do. Okay, so that is a super duper common thing. And there's related stuff in terms of semi-supervised learning where you don't necessarily have hand labeled data. You do things like deleting a word where you've basically created a hole, but you know what the answer is because you were the one that deleted the word. So therefore, you have that. All right. So so again, this section was about transfer learning and using pre-trained models. This is, I'm going to guess, 99% of the time, what you're going to do is you're going to start out with something that somebody else built. You're not going to start out from scratch. The next section is optimizers. We're running short on time. I don't think it's super important to know the math. If you're interested, it's a cool thing. But basically the idea is that gradient descent works really well with neural networks, but it can be slow. So what are some of the tricks? Okay. One of the ones is momentum. And the book says that if you imagine like walking downhill in the real world, okay, if you start in some hills and then you get to a flatter section, that's a plane, the gradient will be very small in the plane section where it's very flat. If you have this idea of momentum, then you come rolling down the hill like a bowling ball and you keep your momentum for a while in the flat section, and that'll keep you going. And so that's one of the nice things about momentum, is that it doesn't slow down right away as soon as you hit a small flat region. It keeps going. The other thing that momentum's really good for is that it smooths out zigzag patterns. So this is a diagram from a different book, but if you start here in the lower left corner and you just follow gradient descent, the orange line shows the actual gradient at each of the points. And at a certain learning rate, you're going to see it's going to jump back and forth across sort of the main axis of this oval. And it will go ahead and converge at the very center of this oval, but it's going to get there a little bit more inefficiently. If you imagine just averaging these things out with momentum, then the upward from this first step will get averaged with the downward from the second step. And by the time you get to the third step, the momentum is going to be more or less taking you straight to the right instead of a lot of up and down. All right. So for me, that's a good visual intuition about why pretty much everybody uses momentum. I don't think anybody uses, I can't think of an optimizer that people use to do gradient descent that doesn't have any momentum in it. Okay. The book talks about several other things and builds up to this idea of Adam. So variance of Adam is by far the most popular optimizer used. I would say it might be 99% of the time people use some variant on Adam. So Adam has momentum. And if you look at the exact formulas in the book, you'll see in the last step, there's this element-wise division. Okay. So if your data is 64-dimensional data and you have 64 floats in it, what it's doing is it's scaling each of those 64 numbers separately. All right. And what that does geometrically is, if you look at this diagram, the idea is that the x-axis here, the left-right axis, it would actually shrink more. And then the y-axis, the vertical axis, it would shrink less. And it would turn this oval into a circle. And the nice thing about a circle is that all the gradients point exactly to the center of the circle. Whereas on an oval, you can see at any point, the gradient doesn't point exactly at the center. So when you're pointed directly at the center, it converges a lot faster. So that's the thing that Adam does beyond just simple momentum. Okay. Adam W, you will see, gets used by a lot of the large models. So LLMs, I'm pretty sure the default for all of them is Adam W. And the weight decay is a form of regularization. So you can imagine that even if your gradients are in that negative region where it's very flat, okay, and you don't have a lot of signal, the weight decay is going to cause all of the weights to shrink by a tiny little bit each time you do a gradient descent step. All right. And that's going to force things to change, even if you don't have a gradient signal. Now, if it turns out that you're really, really close to the minimum and you don't want to, then basically what happens is weight decay causes all of your weights to get a little smaller. And then in the next optimization step, you just push things back to where you were. So as long as the weight decay is small, it's slow. If you're multiplying it by 0.99, whatever, then in the next step, it can just say, oh, that was a bad idea, and I just want to go back to where I used to be. But if you're in a flat region, then sometimes what that does is that helps get you out of that flat region. And then all of a sudden you start learning some more. So not necessarily going to be needed if you have a small model with 10, 20 layers. But once you get to giant models, then this is one of the things that seems to both regularize and also help things not get stuck. The book mentions some of the other ones. Some of this Nesterov accelerated stuff is popular, and Armis Prop also had a bunch of fans, so you may see people talking about that. It's not as popular now that almost everybody uses Atom. I also wanted to mention Muon. which came out this year. So it's too new for this edition of the book. But basically, the thing that the muon optimizer tries to do, at least my understanding of it, is I said that what Atom can do is it can squish the left-right direction to turn this oval into a circle. If the oval were diagonal, instead of being like it is mostly here horizontal, then if you squish the left, right, or the up, down, it's still an oval. There's no way to turn that into a circle. And what muon does by using a very different technique is it can actually take ovals that are not aligned just vertically or horizontally, and it squishes them also to be circles so that your optimizer. And so I think Kimi was the first model that really said, the first LLM that said we're using muon and it works a lot faster. And people are still experimenting, so you'll see muon clip is a variant that has gradient clipping. And an interesting thing is there's an implementation of the muon optimizer early on when we talked about fan in and fan out. Okay, a common early technique was you just use the average and you kind of set things up. What muon does is it actually looks at each layer and it sees what the fan in and what the fan out does, and it actually has a little thing it does where it looks at the ratio of those two and it scales the learning based on that fan in fan out ratio. So effectively what happens is every layer gets a custom learning rate based on your overall learning rate. And if the fan out is really large and it has lots of inputs, then it shrinks that a little bit because it knows you're getting a really large gradient signal. And if the fan out's very small, then it actually, relatively speaking, boosts it. And so I was, just because this was always a really interesting trick in my mind, I was kind of tickled when I saw that the implementation does that. So early on, really, we're just talking about one learning rate that's applied to all of the layers equally. And then we're trying to scale the data with things like batch norm so that it fits with this one learning rate. And so now we're getting even more sophisticated. So now we have optimizers that say, basically, without you having to write a line of code, they're essentially doing a custom learning rate for every single layer, which I think is just really, really awesome. Okay, we're over time. Speeding up here. Learning rate scheduling, I don't think there's too much we need to talk about this. You will want to use a learning rate schedule. This is not something you can avoid, but this is not the most important thing. This is probably the thing in this chapter that least impacts the quality of the final model that you get. And the idea is that once you have momentum, the book mentions that when you get close to the local minimum, once you get to the bottom, the momentum will carry it past that bottom. And so that it has a tendency to just ping pong back and forth around the bottom, but not actually get to the bottom. By shrinking your learning rate at the end, what you do is you're just manually shrinking the size of the steps. So it's still going back and forth, but as your learning rate drops, if your learning rate drops to 1/10, 100th, then it's going back and forth only a teeny amount, 1/10, 100th, as much as it otherwise would have. And so it's effectively settling into the very bottom. So that's the idea of having a lower learning rate. You can actually experiment early on when you're playing with things with just a constant learning rate. You don't even need to have something that changes over time. But for a final model, it is by far, I think, the universal best practice that you lower learning rate at the very end. And the question then is, well, how do I learn it? Is it a curve that looks linear? Is it a curve that starts steep and gets flatter, starts flat, gets steeper, or whatever? And one of the most common ones is cosine. So it starts out kind of flat, then it gets steep, and then it ends up pretty flat. I also mentioned here that like Jeremy Howard trained a whole bunch of computer vision models, and one of the things that he found work was not just going from big to small once, but actually repeating it. So maybe you go from 1e minus 3 to small, and then you restart the process all over again, where you go up to like 3/4 of that and then go down, and then half that and go down, and repeat this cycle a few times. And so there's some analogies to like metalworking, annealing, simulated annealing of metals and things like that. Okay. Yeah, go ahead. No, that's not what I'm saying. They seem to have a different name for it. I can't remember what they called it in the chapter. But one of the techniques is you look at your loss, and um, when you're not making progress, then you lower it a little bit, and then in the end, at some point, eventually, you will shrink down. And so I know of it as like reduce on plateau, but they had like a slightly different name in the book where they said basically, um, go for a while. And again, by starting big, there was a question about like not getting stuck in local minima. So a large learning rate at the beginning will just fly right over really tiny potholes that are not really your low points and follow. You want to go down the big hill that the road is on. You don't care there's a little pothole in the road that's a little bit lower than the rest of it. So that's what high learning rate does early on. But eventually, when you're kind of at the bottom of the basin, now you're looking for the smaller, the lowest best of the best. And so that's when you need to slow down and kind of like try to work your way. So I think of like the moon, right? You want to get to like the low basin, and then you want to get to the bottom of a big crater. But within the big crater, there's little craters or medium craters, and you want to get to the bottom of one of those. And then within that medium crater, there's going to be little craters. And so that's why you're slowing down and ultimately taking smaller and smaller steps to hopefully then find the bottom of the little crater that's at the bottom of the medium crater that's at the bottom of the big crater that's at the bottom of the big basin. Sorry, what was the question? So the momentum is not something that you set. The question was about relationship between momentum and learning rate. The momentum is just basically if you use the physics analogy, right? Momentum and velocity, right? Momentum is just continuing at the same velocity that you were earlier in time, and that's what momentum is here. Is it's basically you're continuing to take steps in the direction that you recently took, even though your current direction. So your gradient may say go east, but if you've been heading north continuously the last few steps, you're going to go northeast instead of just east. Okay. And so the momentum is defined by what you did last time. It's not a manual thing that you scale. Okay. Yeah. Thanks for the question. All right. Last section, we always talk about overfitting. So there's some very important techniques, and we will continue to talk about overfitting as we get into the other chapters. We talk about special architectures. There's some things that are more common for like computer vision models, some things that are more common for language models. We'll get into that. Just like with small models like linear regression, you can do L1 and L2 regularization, where you basically say, I'm going to penalize you for having large weights. And the same intuition that applies with linear regression applies here. So for real world problems, you tend to want to have a small change in your output if you have a small change in your input. If you had a giant weight, if you had a weight that was 1 million, then if you move your input by 1, your output changes by 1,000,000. Okay. Most real world problems don't have those kinds of properties, which is why we find forcing your neural network to have small weights tends to be a good way to get generalization properties. You see it, it's not like I would say super common, because there's other things you can do, like weight decay. So Adam W. Dropout is a very important concept to understand. And it's kind of crazy in my mind because it's super destructive. So you imagine you do dropout at 40%. I mean, that's crazy. That's like very catastrophic hacking of your neural network every time you do a training step. And yet, it turns out that, like, famously there was whatever, the model that was trained a long time ago just held like US tanks from Soviet tanks, and the Soviet tanks, almost all the images had snow in them, and the US tanks, none of the pictures had snow in them. And so the model was not looking at the tank, but was looking at the background to see how much snow was in the picture. Okay. If there was a part of your network that's looking for snow in the pixel in the upper left corner, okay, once you do dropout, that pixel, that signal is gone. And then that would mean that the model would have been forced to pay attention to the rest of the image, hopefully the picture of the tank. And so it's not necessarily even 100% of the time that that particular thing gets dropped out. But when it does get dropped out, it's forcing the model. So it's really hard to overfit on these kind of random correlations. And so this is where you could see that if you had a model that really was wanting to just say, I see snow, a higher dropout rate, like 40%, would mean that 40% of the time when you train this model, it needs to learn based on something else. And so then hopefully that 40% of the time is going to pay attention to the tank, and it's going to learn good things. And once it learns good things, it might actually learn them so well that even once this snow neuron is on, it realizes that's not as important. I can actually lower my loss by paying more attention to the shape of the wheels than paying attention to whether or not the upper left corner has snow in it. Okay, so that's why we see dropout. And I think it's important to understand this concept because it affects a lot of things. So it adds so much noise to your training. So when you look at your train and your loss training curves, the loss on your train curve is generally going to be quite a bit higher than your validation loss because we're adding all of this noise by whacking out huge portions of our model. You need to understand this, okay? Otherwise, it would be very unusual to say, well, why is my model doing better on my validation set than on the training data it's seen? It's not technically doing better. It's just that validation doesn't have this weird dropout, okay? You can also run into some weird issues where if you're just testing things, whether or not you have set it to training mode or whether you've turned off training mode will automatically in TensorFlow or PyTorch will automatically turn off dropout when you're not doing training. And so if you don't understand that this is what's going on here, there's going to be like these weird different things happening with your model, and it can be very confusing at first if you don't understand that your model is physically changing. Everything else we've talked about now, kind of everything flows the exact same way, whether you're training or you're doing predictions. But in this case, once you're using a model with dropout, you get these different dynamics, and so you don't want to get accidentally tripped up by that. Haven't shown a lot of code, but just another snippet here so you can see in here we just say layers dot dropout and then what's the rate. So 0.2 would be 20% of the time. There's the business they talk about where if you drop out 20% of the inputs to the next layer, then you probably want to scale your data up by about 20% so that the overall size of your inputs doesn't change. And so this is nice where you can actually change the amount of dropout and it doesn't really affect the inputs going to the next layer. Just wanted you to know this is all implemented by the libraries. So PyTorch or TensorFlow do that. And you just have to say, I want a dropout layer. You don't have to tell it to do it. It does it all automatically for you. The whole training versus not training, all of that happens automatically for you. You don't have to worry about that. Super quick, but I did want to mention that sometimes by default, dropout is just this node by node thing, but you might want to do dropout in bigger chunks. And so you can actually do that. And that's an interesting thing where, say, you've got 3 different branches and you can just drop out an entire branch instead of worrying about dropping individual nodes. And that at that coarser granularity, that might be something you sometimes want to do. I don't think Monte Carlo dropout is important, but personally, I think it's wicked cool. The idea that somebody figured out, oh, we can actually use this dropout thing a lot like a random forest model, where we just get a whole bunch of ensemble independent predictions, and we can see what's the average of these predictions, and we can even see how much spread there are. So hypothetically, you do Monte Carlo dropout, and your model says, I think it's a cat, and it's 95% likely a cat on average across 100 different runs, and the standard deviation is really tiny. That means, like, holy cow, that means that every single one of those 100 probably had a value close to 0.95. This model's like crazy confident. Doesn't for sure mean that the model's right, but it does mean that the model's for sure very confident. And then the very last subsection is this thing called max norm regularization. And I had actually never even heard of it. I'm assuming it was in the earlier edition of the book that I read, and it must have gone in one ear and out the other. So I checked with Ryan, and he said, no, I don't think you guys need to even know what this thing is, because nobody's using it anymore. So I would not worry about that. So overall, at the end of the chapter, they have these guidelines. They're pretty good. The tweaks that I would make is, yes, do the initialization that they say, except you don't have to actually do it. It's the default already in PyTorch and TensorFlow. So it'll automatically be there. And then for learning rate, I'm not quite sure. I don't know if anybody online or in the room knows, but I think cosine for me is the conventional wisdom default. And I don't know why the author didn't mention cosine.
Cosine wasn't that popular up until somewhat recently. There was a period where like everyone was using reduced learning rate on plateau, and then it really depends on how much data you have and how much you know ahead of time. If you're training something for a completely unknown number of epochs, then it's very hard to do cosine correctly, because you're assigning ahead of time, I'm going to follow this curve during this training procedure. And so if it turns out you set it for 1,000 epochs and it finds its best value at 100, then it's difficult to actually set that ahead of time. So there was a period where everyone had small data and everyone was just doing reduced learning rate on plateau, and that seemed good enough. But then now with LLMs and all that other stuff that people are training, it's like we know we have this amount of compute budget, so we're going to train it this number of steps. I want it to converge the most at this point, basically.
Cool. Yeah. And I guess people these days do a lot more in terms of, I will train a smaller version of my model and kind of learn the dynamics, learn whatever. And then, like you say, once I know my compute budget for the final thing, then I can just predictably use my cosine. Okay. Awesome. Thanks for those of you who stayed late, stayed extra. The exercises, questions 1 through 7, just recap understanding this chapter. One thing we didn't talk about is you cannot initialize your weights to be all the same, because if they're all the same, then they will all get the same gradient and they'll stay the same after every step, and they'll never ever not be the same. So in case you're wondering, like, that's why it's always random within any given layer, within any given weight matrix. And then exercise 8 has you practice playing around with these a little bit. And what you can do is you can do all the code completely by yourself, but also, since the author's repo has all the answers, you also can choose a point in between writing all the code yourself or just looking at some of the answers that the authors provided. All right. Thanks, everyone. I really appreciate all the interaction, all the questions. Once again, we normally meet every Saturday, but the next 3 Saturdays are a little bit up in the air. Next week, maybe a Zoom only event. And then we have the holidays and the NeurIPS conference. And so the next 3 weeks are still fairly uncertain.
I have 2 bonus things. So total bonus time, no pressure to stick around, but can you give me permission to share my screen? So these are just links that I put in the chat. So two different things. We talked about activation functions a little bit. So there was this researcher a while ago who made this MISH activation function, and I thought it was kind of silly at the time, but I've referenced this many times, so I actually appreciate their work now. They made this activation function, and I thought it was silly because it was like this swish activation function already existed, and then they said, oh look, MISH is actually a little bit better. And if you look at the details of it, it's like, okay, you change the values of this curve the tiniest amount, and now you're saying everyone should use this. It's a little bit better. But the interesting thing that they did is they tried these activation functions for a bunch of different things, and they showed visualizations of the loss landscape. So this is what we were talking about before. You change your activation function and it changes what this curve looks like. And they also did really thorough analysis of many different domains. So looking at image stuff, looking at text stuff, looking at other kinds of models, and then just saying like apply all of these different activation functions and see how they do. So they have this table here where they basically said, look, we tried all of these activation functions. Here's what the winners and the losers were. So this is something that I look at somewhat regularly, just kind of looking at what the best activation functions were. At this point, pretty much everyone just uses JLU or however you pronounce that one. It's a solid default. So that was it for activation functions. And then one of the things that I wanted to show is there's something similar for optimizers. So I think that these are useful because you can kind of visualize like the momentum and the other things that are being integrated here. So they have two different synthetic tests that they built up. So they basically said, look, we set out this optimization space and we try the different optimizers and what path do they take in order to try and get to the optima. So what you can see here, it's a little bit small, but they're trying to go from whatever the starting point was to the green point. That's what the actual global minimum is. So they made this test pattern where it's very difficult because it's like these up and down, like synthetic, like really bumpy pattern, trying to see can it escape out of these little local minima. And then they have this other one where it's this big wide bowl where it's basically saying, can you go along this curve and not right up on the walls and oscillate back and forth, just kind of follow the curve to the final ending point. So this is interesting because you can look how some of the different optimizers react to things like this. So you can see there's interesting patterns, like this one is oscillating back and forth a whole bunch through this curve. If we look at something like Atom that we were talking about, you can see it follows a pretty reasonable pattern. It's able to find it finds this kind of like gap between all these different things, and then it kind of converges to a good value. So it's the blue dot is the final position that it found after a certain number of steps, and the blue or the green is what it's trying to find. But you can see like there's very different behavior between these, and some of this is determined by the learning rate, some of this is determined by the momentum. Some of it is determined by the actual algorithm. I'll see if I can find one that has. So you can see something like this. This might have had some momentum value and it's approaching this and then it's going over here. And then it looks like it totally overshot. So it kept its momentum too long and it overshot its goal. And then it had to eventually converge back. And so there's just interesting things that you can kind of learn from looking at these. All right.
Thanks, Ryan. All right, we'll wrap things up for today's session here.